Um, We're going to continue this week. I'm actually going to start by introducing a new cipher, the Vignette cipher. So this is a classic cipher that has a lot of power and importance for where we're going to talk about next, which is actually is probability and so forth. Because this cipher seems like it's doesn't like it should be pretty easy to keep secret. So the Vignette cipher is what is called a polyalphabetic cipher. That means that we have a cipher, a running key, and we're using multiple different ways of encrypting letters. So because we're doing polyalphabetic, that doesn't mean I have multiple alphabets, but imagine our pre-alphabetic cipher up to this point in time. So before, if I did something like if I wanted to, let's say, take the word this message. I would encrypt it, and this is not just shift ciphers. I would have something so that all the T would have to go to something. So let's say the T goes to W. Let's say that S happened to go to A. Well, that means that all of the S's would go to A. Similarly, all the E's would have to go to the same letter. We could call it F. And we can keep going through here, and then everything gets a letter. And this is what was vulnerable was that we knew that E is the most common letter used in the English language. So we can look at a message and say, ooh, what is the most common letter in that message? And just break it down using probability. It turns out that that is not how the Vignette cipher works. The Vignette cipher, we are going to actually encrypt it, and that same strategy will not work. Instead, there's some different attacks that will turn out to be quite useful. Now, there's two main versions of the cipher. The first is called a keyword cipher. It just has a simple keyword. The second one is called a priming key, and we'll get to that. Essentially, my message is its own key. That is kind of crazy and weird, but it also lets you pick this out one letter at a time. So let's kind of deal with this and let's talk about how I would encrypt it, but also then how we would decrypt it. So let's do an example. Suppose I want to encrypt yellow dog and I'm sorry, yellow, my keyword is dog. So what we're going to do is I'm gonna lay this out. I'm going to start with yellow as my plain text. I'm then going to write my key repeating as many times as necessary to be directly underneath it. Now, here's what I'm going to do. I'm going to send the yellow, the Y, I'm going to move it D spots. So remember, A was 0, B was 1, C was 2, D is 3. So Y, in essence, we move it 3 spots. So it becomes Z, A, B. And sure enough, so this would become a B. Then we come to E, and we're like, well, where's the letter O? And we shift it that many spots. So O is, remember, is just really the amount of shifting I have to do. This first L will be shifted G spots. The second L will be shifted D spots. And this is where it's interesting because if I actually do all that, boom, I get this. We end up, it's quite easy to then see that we have something that is very different. Even though I have two letters here, L goes to both R and O. That's all. So because L goes to two different values, it now becomes a little bit harder to say, what's the most common letter that occurs? And that's the obvious and clear answer. It's not going to be obvious and clear. In fact, we have to break it down and kind of work on it. So this is the main idea. And I did a very simple example with yellow and the word dog. The more complicated the longer the keyword, especially the longer the message, the better off it is. A short one like this, if I had a longer message, dog would eventually give me an L that goes to an R as well, multiple times over. And then I can start seeing those kind of trends and attack those very clearly. So one of the things that we use sometimes in this is something called a vignette type table. Your book has one of these. You can Google it. It pops up many places. So this is a vignette table. And let me just kind of explain what that means, a vignette table. So our whole first row We get a highlighter and this. So what's it mean? Well, this whole first row is going to be is all of the A values. Notice is what does A go to? So A, if I was to write an A off to the left-hand side, A goes to, well, A. B goes to B because it doesn't shift it at all. So whenever we have the letter A, we usually don't consider this table. A better way to understand this table would actually be if I go back just real quickly to the previous page, Y and D. So what I do is I'm going to come here, and how do we get B? Well, if I took the Y column and I'm going to highlight the entire Y column, and then I'm going to highlight the entire B column. I didn't want the B, excuse me. I want the D column because dog is our first letter. We'll notice that where they intersect is the letter B. And sure enough, that is why Y became a B. Now, this table is also useful because if I got the previous message, so let me undo this and go back to the previous. If I got this message down here, how do I unencrypt it? Well, I know that I would have to know the keyword is dog because it's a symmetric system. But I know dog, so what I do is I come to the table of the D table because the first letter is dog. And I come along this thing and I'm like, okay, where is the letter B? And I see the letter B all the way over here. And because the letter B is right here, it means I have to come up and that's a Y. Then I come to the next letter, which is O. And I'd come along and I'd be like, okay, where is the letter S? And it turns out S is here, come all the way up. Oh, that's an E. So we can undo this thing again by simply knowing the key word and leveraging that over and over and over again. So that's a keyword strategy. Now, there is a way to actually design this programming wise. I'll let you kind of figure out that subtlety. It's really kind of a heads up. It does involve modular arithmetic. And it's actually, you can do a modular arithmetic. There's also a dictionary style, a couple different options. All right. So another key thing to talk about is what's called the priming key. Now, a priming key is we are going to actually use our message as the key. So to see this, I'm going to take the message plain leave at midnight. Well, I'm going to get rid of my spaces and I just have leave at midnight as one giant solid block of letters. What I then do, and this is where this gets fancy, is I start off with putting Z down. Now, this is how I encrypt it. And then I put in the rest of, oh, my apologies, that should be a G and H in the last two spots. I put down the rest of the word. I just do leave at midnight. Now, I start over the priming key of Z. Your priming key could be 3, 4 random letters. It doesn't have to be just one letter. This is one of the strategies. And then I come through and do the exact same thing and undo the cipher. And L by Z goes to a K, et cetera, et cetera, et cetera. You just keep going through all the things. And so we have this ciphertext down here on the bottom. Now, here's the problem. So how do we unencrypt this? That's what you're probably asking. Well, let's say that I get this text. I get a K, and all I know is that the priming key is Z. Well, what I do is I have to come back to this Vignette type table right here, and I'm going to, again, remember I got a K, and I knew the priming key was Z. So I'm going to find my Z row. I'll come along until I reach a K, and then I go up and I get an L. Okay, so I now know that my next letter that I'm using in the encryption process is an L. So I then come on the L row until I come over to the letter that I'm looking for. And I would just use this row, and I'd go find what was that letter at. I remember it was leave, so that would be turns out it was this P because it was E, the very next letter. And that would give me an E. So then I do the next one. I'd come along the E row and just sit there repeating each. You have to find it one term at a time because each term tells you how the next one unlocks. And it's not just a fixed, it's going to go by this value. So what we have to know which one are we applying to and go from there. All right. I hope that helps you understand how the vignette tables are. I'm going to give you a little bit of assignments to play with it. I really want you to try to do it without like Googling a ton. I want you to think about this thing. One of the key things is ask the question of why is this a super powerful, why is this beneficial? And I will give you a heads up on that just real quickly. We even come back here again to the sleeve at midnight. I'm going to point out real quickly using my highlighter that I have A and it's going to both, I have an E and this A is also going to an E. That's slightly problematic. My E's, on the other hand, let's change colors to a blue. They are going to a P, a Z, and I don't have any others. My I's, let's again change colors to an orange. My I's are going to a U and a V. So we can sit here and repeat this process and notice that T's, well, they are going to T and an A. Huh. Hmm. And from here, we start asking all sorts of questions like, so it clearly, like sometimes we had the E, A went to E both times. Some letters don't go to things. And this is why it becomes kind of tricky, is that you can't simply use this direct probability distribution saying, okay, this one occurred 33% of the time, so that if this letter occurs 33% of the time and it occurs 33% of the time in a message, it's this letter. We actually have to do sometimes what's called a collision attack or some other strategies to kind of figure out how to get at this thing. There's one other attack, and I want you to think about how much information does Eve need to get to figure out the key? I mean, obviously she can see the ciphertext, the end. How many ciphertexts does she need? And does she need any plain texts? Ask that question. That's your key thing to think about. All right. Good luck. And again, let me know if you have any questions.